And good afternoon to everyone. We're going to do our Snack and Learn webinar about climate change models, a selection methodology that we developed in the office in Santiago. So first, about us, my name is Hernan Morales. I'm an hydraulic engineer. I've been in WSP for 2.5 years, mostly in projects about hydrology and climate change studies in Chile and South America.
I'm Ignacio Toro. I'm a hydrologist and climate change specialist. I have been working in this kind of projects related with climate change for around 6 years. With Hernan, we belong to the Chile and Argentina operation. We are around 1,600 professionals in 4 offices: Santiago, Concepción, and Puerto Montt in Chile, and Mendoza in Argentina. We're part of the surface water team based in Santiago. We are 33 water resources specialists. We have a strong experience in water balance, hydrological and hydraulic models, flood assessments, and of course, climate change projections. As part of our climate change services, we evaluate different climate change scenarios, a high number of climate change models to characterize the uncertainty of the climate change projections. We study the projections over precipitation, temperature, and other meteorological variables. We have a strong knowledge about different bias correction methods and downscaling statistical methods. And we have developed some climate change model selections methodology according to different statistical techniques. Some of them we will be review today. And based too in risk appetite and different objectives of our projects. Our climate change assessments are related with hydrological studies in the water team. We analyze the impact of climate change over water balance, groundwater recharge, water availability, over extreme hydrological events, for example, probable maximum precipitation, probable maximum floods, and we evaluate current and projected infrastructure response to extreme hydrological events under climate change. Today we will talk about the general context, the GCM selection criteria, results, and finally closure and Q&A. As a general context, we assessed climate change for a mining operation in central Brazil. As you will see on the right, this operation is based on the Goiás state. They have been experienced a reduction in precipitation and a rise in temperature. So it's really important to assess the potential effect of climate change over these 2 variables and the impact over water availability. So the client asked for historical and future characterization of the area, water availability projections, extreme precipitation projections too, to evaluate different infrastructure, and the selection of 3 climate change models to be used in a water balance model. So you should be asking, why would you want to select climate change models? So the answer for this question are multiple answers. For example, in the mining industry, you have to fulfill different standards like Global Industry Standard on Climate Change Management, GCM, and the guidelines given by the International Council on Mining and Metals. So you need to assess climate change, assess and evaluate the uncertainty of your climate change projections, and take some decisions. You have to take some decisions about the future to evaluate different kind of projects. So for me, one of the main reasons to select climate change is related with the high uncertainty of the climate change projections. As you will see in the upper right figure, at the end of the century, for total annual precipitation projections, you have a really high uncertainty because you will have a reduction of 20% to an increase in 40%. So you should be asking, okay, I have to use the average of these models, the worst or the best case. How could I take some decisions based in that information? And you have multiple models that are, these are the gray lines, and you have multiple climate change scenarios. So you have different sources of uncertainty, and you need to first characterize this uncertainty and then have take your decisions. So in a more specific way to this answer, you should select climate change model, for example, to generate inputs for water balance modeling or evaluate solutions to increase resilience or water availability. You could evaluate desalination plants or put a new water reservoir or explore groundwater supply, for example. And of course, evaluate extreme hydrological events, focus on design of infrastructure. As you will see in the bottom right, we select climate change models to evaluate the response of existing and projected infrastructure over extreme precipitation events with different results over floods. So for this kind of study, we cannot evaluate all the climate change models and all the uncertainties. So we need to select one or two climate change models.
So now we are going to the main focus of the presentation, the model selection criteria. As a little preamble, there is no GCM that is completely accurate or valid for all regions. Because of this, you want, or is a general recommendation, to use as many models as possible to see the general trend. But sometimes you need to select or discard some of them because you want to face uncertainty or you want to select only some series of climate change models. For this, the IPCC gives some general selection criteria that are here. There are four main focus. The first one is vintage. It's trying to use the most recent models. This is because they are based on the most recent knowledge. The other one is resolution. It's trying to use the models with a higher resolution because it's more likely they represent better a specific location. Then is the validity, which is one of the main focuses of this presentation, is use some statistical tests based on performance for the historical period to see the performance of the models. Why is this? Because if a model performs well in the historical period, it's more likely, not sure, that it will have a good representation or behavior of the future. And finally is the representativeness criteria. Is from all that you previously pre-select, you want, depending on the focus of your project and your level of risk or your risk appetite, you want to finally make the selection that you want. And all of this was presented in a Chilean technical conference that will be in the presentation if you want to have more details about the validity test that we use. So about the validity test that we develop, there are a few ones. There are ones that are more general that you can use, for example, seasonal and trend that we are going to see in the next slides. You can use for all kind of studies and all kind of variables. And they are more statistical, but there are some others that we develop specific for hydrology. That could be the Markov matrix validation that was developed for water balance modeling. And there are another ones, for example, with daily criteria that, for example, frequency and coefficient that are focused on extreme events, in specific for extreme precipitation. But the application of one or another will depend on the focus of your project. And this could be relaxed, or you can add more tests, or you can modify some of them. How about the first validity test is the seasonal validation. We analyze the monthly distribution of the variable we are analyzing. In this case was precipitation and temperature. If you focus on the graphs in the left, and there is the graph of the dimensionless precipitation. The green line is the observed data, and the gray lines in the background are the climate change models. If you notice here, there's a good fit between the climate change models and observed data in this case. But if you see below, for the temperature anomaly, some models don't have that great fit. So how do we study or analyze the performance of this? We use the Nat-Sutcliffe coefficient. In these graphs, we have two graphs. One in the left is for the raw GCM data, and the one in the right is for the corrected data. In the x-axis, we have the Nat-Sutcliffe for temperature, and in the y-axis is the Nat-Sutcliffe for precipitation. When we have a number one Nat-Sutcliffe, it means we have a perfect fit between, in this case, of the observed data and the GCM simulated data for the historical period, which is the base that we have to compare. The gray triangles are the GCM models. The red lines here are the filters that we apply. Depending on the main focus of your project, maybe it's more important the seasonal validation, so you can do it more strict, or you can relax this. It will depend on how many validity tests you apply, or what is the main focus of your project. You only have to try to not end up with zero models at the final. So the red lines are is the filter. Everything outside the red box is discarded, and the same happens with the corrected data. But if you focus here, all of the models have a perfect fit for the Nat-Sutcliffe, and this is because one of the objectives of the correction was the monthly values and distribution. So this means we did it well with the correction. Now about the trend validation, we analyzed the annual trend of records of the variables. In this case was precipitation and temperature. If you focus on the graphs in the left, here is the annual precipitation, and below is the annual temperature. We analyzed the records with a Van Kendall trend to see if it was a statistical significant trend. In the case of precipitation, it was significant with a decreasing trend, and for temperature, it was a significant increasing trend. So we want to reproduce the same in the historical period for the GCMs, and for this are the graphs that are presented. The first one in the left is for the raw GCM data, and the one in the right is for the corrected data. So we have the climate change models, and in the triangles here, the green point is the observed data, and the filter is the red lines here. So in the x-axis is the temperature trend, in the y-axis is the trend for precipitation. And if you notice here, the observed data, as we previously said, have an increasing trend in temperature and a decreasing trend in precipitation. So we want to have the same in the climate change models in the historical period. So we put a filter here for all models that have an increasing trend in precipitation, values bigger than 0, and decreasing trend in precipitation, values lower than 0 here. So everything outside the box is discarded. Same for the corrected data here. But as I previously said, this will depend if you see a statistical significant trend, and maybe you don't see this in precipitation, for example, and this will be open. You don't discard, for example, these climate change models. Well, now we go with the other criteria, the representativeness. After you do the the pre-selection of models with the validity test. You can add or use more validity tests. You want to end up, in this case, with 3 series of climate change models, and this will depend on your risk conditions. And the main focus of this project in particular was water availability. So we needed to analyze how many water we will have, and for this we use the aridity index, because with this index we can map precipitation and potential evapotranspiration, and even give it a climate classification. So it was a win-win in this project in particular. And to analyze the risk condition of models, we make this graph, which has the aridity index projections. In the x-axis is the aridity index for the first time window. In this case was 2031 until 2060. In the y-axis is the aridity index for the end of the century window. And here are the climate classification of the aridity index. We have humid climate here is the limit, and dry so humid climate too. So when we have a bigger aridity index, it means we have more humid conditions. In this case, if we go to this corner, we have more humid condition. And if we go to the other corner, we have more dry conditions. All of the climate change models we analyze in the validity test for the 2 scenarios are in the blue dots here. The historical data is represented with this green dot. The pre-selected model are these yellow dots and the orange ones, and the final models selected were the orange dots here. So from all the pre-selected models, the one pre-selected with the validity test previously, we want 3 conditions in particular for this project: 1 optimistic, 1 severe, and 1 extreme. So for the optimistic one, we analyze this aridity index, and we notice here that there is a model close to the historical data, which has a little increase in precipitation and a little increase in potential evapotranspiration. So basically, the optimistic scenario here is practically the historical or what we are seeing today. The more severe scenario is close to this percentile, and it shows a decrease in precipitation and a really big increase in potential evapotranspiration. And finally, our extreme scenario in this case was the F goals, with that even changed the climate classification given by the aridity index, and it presents a big decrease in precipitation and a big increase in potential evapotranspiration. And as I previously said, this criteria in particular will change depending on your risk appetite or the objective that you have on your project. So a resume or a closure to the presentation. See, as I previously said, there is no GCM that is completely accurate for or valid for all regions. So it's a good practice to see the general trend using as many models as possible, but sometimes you want to face uncertainty. And for this, it's good to have a selection criteria. Another thing is that the methodology that we presented is robust because it helped, as I said, facing uncertainty and use climate change for decision making, which is the main focus of every project. And there are some examples that I want to remind you that this methodology could be used for, that Ignacio previously said. That could be generate inputs for water balance modeling, characterize extreme hydrological events, or evaluate some solution for increasing resilience or water availability. This will be, for example, desalination plants, water reservoirs, groundwater supplies, or another ones. And as a final point of view, the tests we show you are just general recommendation. and you can add or you can modify some of them depending of what is the main focus of your project. So these are our contact details. If you have any more questions, you can contact us or to contact the office in particular. And you can leave the questions that you have now in the chat, and we can start with Sharon. You can help me with the Q&A.
Yes, of course. Thank you, Hernan and Ignacio, for a fantastic presentation. Just to mention, like Hernan just mentioned, you can continue to log your questions in the question box on the control panel, and also you can find there the presentation slides as a PDF. I will start with the first question. Are there specific models suited to different geographies?
Yeah, I think I can answer that question. As I previously said, there is no model that is completely accurate or valid for all regions. So you need to test it with a test validation or validity test. But there are some models that were developed in specific locations. For example, there are some models from China and other ones from the UK, I think, and maybe one from Australia. So maybe that models will represent better the conditions there. But in general, you still need to understand and analyze the projections and the historical data.
I will add that we usually, when select climate change models, we first think of the performance of the historical period of this climate change model against, I don't know, the historical observations or local meteorological station. But we need to keep in mind that the real value of the climate change model is about the projection, and we don't have any test that could evaluate the performance of the prediction of the projection, because the climate change model don't predict the future. It's just a projection based on different climate change scenarios. So it's really important to keep in mind that every climate change models means different risk conditions in the future, and this risk condition could be outside the general diagnosis of the climate change, for example. Then you need to evaluate as many models as possible and more than one climate change scenario to characterize the uncertainty and know if this climate change model represents what the average of the projections, the maximum, the minimum. It's a severe case, extreme case. You need to keep in mind that.
Thank you. The next question is specific to Chile. It mentioned it reads like this: in the Chilean North Atacama Desert, especially in the intermediate and high mountain area with the monitoring deficit, what should be the priority in the selection process?
Yeah, in that case, with a great altitude, you have another type of objective in general for your project in particular, because maybe you don't see precipitation all year, for example, so you don't have any sense to make a trend or a seasonal validation of precipitation. Maybe you want to analyze extreme precipitations, for example, which is one of the validity tests that we develop. And maybe you want to pre-select or select some models with another variables. For example, you can study temperature or potential evapotranspiration in that case.
Thank you. The next question is, what is the scope and limitation of the proposed methodology and the consequences of limiting the amount of conditions analyzed?
Well, the limitations are depending on your study. These, as I said in the presentation, are just general recommendations. So you might want to add or don't use some of them. And the tests that we develop are main focus on hydrological problems. So if you have another type of project, they might not be as useful, but still we do some validity tests from general contexts that are more statistical, so you can use that still. And about the problem that you can have if you put if you are using just one scope for the validity test, you might end up with just one condition to the representativeness criteria, and you might end up with just I don't know, a group of models that simulate increasing precipitation, for example. So you have to study well or do a good analysis of what validity test you are applying and how restrictive or you are applying it to this project in particular.
Yeah, I would like to add that the climate change selections methodology is a site-specific and project-specific approach. As Hernan said, we usually select climate change models based on for what are you selecting climate change models. If you are selecting climate change models to, I don't know, evaluate the water availability in the future to, I don't know, for supply, for example, you need to assure the water supply. You don't select a climate change model that tells you that the water will be suffering an increase in water availability. You need to select based on the risk that the climate change models represent. So depends on the site and depends on the project.
Thank you. The next question is about the comparison with the local models. How well does this method compare to local models? Are there particular regions where you would strongly defer to local models?
I could take that. It's a really good question. We usually have the GCMs, the global climate models, have a low spatial resolution, so they cannot represent well the local conditions. That's why we evaluate, for example, the seasonality with a dimensionless value, not the direct value. And there are some regional climate change models or local models that are developed for I don't know, different countries. In Chile, we have some experience with that. We have a model. It's called Rex CM4. And okay, if you have a local model, you will expect a better representation of the historical behavior, seasonality, trends, the number of days with precipitation, and etc. But you need to keep in mind that you don't know if a climate change model or a local model or a regional model represents well the future conditions that you will expect. So maybe the local model or the regional climate change model represents excellent the historical behavior of the climate, but it's really bad representing the projections. How could you know if a climate change model or a local model, regional model, it's bad or maybe gives you a projection that it's too high or too low? Comparing them with more climate change models, then you will know, for example, okay, precipitation could be a decrease of 20% and an increase of 30%. My local model says an increase of 100%. So there you could see that your model that represents really good the historical behavior, maybe it have some problems around numerical problems or another source could be to represent the future projections. So a local model is a really good point of start, but you could not assume that your local or regional climate change model it works perfectly. Okay, you need to assess the climate change uncertainty. You need to assess more than one climate change scenario to know what could you expect in the future.
Thank you. I will take the last question. What tools can be used to assess the impact of climate change, and will the utilization of atmospheric variables from GCMs help?
Well, I think I can take that question. Climate change models today are the best tool we have to see future projections. So basically, they are the best tool we have now. You only need to remind that they have biases because they are global models. So you need to do corrections with local information.
Fantastic. Thank you very much. Thank you everyone for all your comments and questions that we received during the Q&A, and apologies for not reading all the questions that were sent. The presenters will be coming back to you this week with all the answers. So thanks again everyone for attending this Snack and Learn webinar. Please feel free to follow up with Hernan and Ignacio via the contact details shown on the screen. And we hope to see you in our upcoming sessions. So thanks again everyone. We will wrap up the session now.
Thank you. Bye.
Thank you.